All right, Rad Nation. Today we're talking about fluoroscopy, especially image intensifiers and their role in modern fluoroscopy. All the great details about how you actually convert from X-rays, you get electrons, and then those electrons get amplified. Coming up here at How Radiology Works. Imagine you're a new radiologic technologist student, you're walking to the hospital, you see some different systems. You see a system that looks like this, or you see a system that looks like this. Are you going to be able to tell these apart? Can you tell that these are actually two fundamentally different technologies to do the measurements? The biggest thing you can tell right away is actually not on the X-ray tube side, right? The X-ray tube is actually down here. On the X-ray tube side, they all look fairly similar, but it's actually on the image receptor. It's on this side here. These are what's called image intensifiers, and they're actually kind of bulky. So the X-rays are coming in, and then along that direction in which the X-rays are traveling, you need a fair amount of actual electronics to actually end up amplifying the electron signal that we're going to talk about here. And on the other hand, on a flat panel system, it's actually much thinner in that direction because the panel is actually flat. You're actually converting from the X-rays to your digital signal with fewer steps and without as much need for the bulky electronics. Flat panel over here and image intensifiers over here. So that's step one, be able to identify a difference just based on looking at them. And how does the image intensifier work inside? What's actually making it need that significant depth there? So if you have your, what we call the remnant X-ray beam coming in right here, after that remnant X-ray beam comes in, the first thing it's going to hit is actually this grid here. This is an anti-scatter grid, so we're blocking some of the X-rays, and we're preferentially blocking those X-rays which are not coming from the location of the actual source. So in this way, we can try and reduce the amount of scatter that's making it into our image intensifier. This gray structure right here is the vacuum tube, and the vacuum tube does what it says. It keeps everything in a relative vacuum, so many fewer molecules there, so that the electrons will be able to travel relatively well within this vacuum tube. Again, this was the anti-scatter grid we talked about. Here is the outer housing. So the outer housing surrounds the whole thing, and then this is going to be a relatively thin layer of metal. So that is one disadvantage of this image intensifier, namely the signal from the X-rays has to pass through this outer housing in order to actually start the measurement chain. So there's actually no benefit for passing through the outer housing, but only a loss in terms of some of the X-rays are going to get lost in that outer housing. That's an advantage of the flat panel system in that you don't need to have this kind of separate outer housing. But then after they pass through that outer housing, we have what's called a photocathode right here. Then we have an anode right here. So just like if you've seen our video on the way that an X-ray tube works, your electrons are generated at the cathode. This is called a photocathode. We're actually going to make photons first, and then it's going to be a cathode making electrons. So photocathode, photons and then electrons as in that cathode. So we're going to have those electrons. We're going to then need a way to pull the electrons across. So just like we have in our X-ray tube, we have a bias across here. So we have about a 25 kilovolt bias. So again, a fairly significant bias or electrical potential that's going to help pull those electrons across in the image intensifier. Then what happens inside that photocathode, the X-rays come in, they're going to hit an input phosphor. That phosphor is going to convert them to light, and then at the photocathode, that light is going to get converted to electrons. So now we have an electron signal which is proportional to the remnant X-ray beam. So we want something that's proportional to the remnant X-ray beam. So one option you could obviously think of is actually just have a phosphor and then just point a video camera at the phosphor. But we actually want a method to amplify the signal So that's what the purpose of this image intensifier is. We want something to actually amplify the signal, so we're converting to electrons, then we're going to impart those electrons with a lot of energy, and then we're going to convert them back to photons. The process in which they're getting converted to a lot of energy, they're getting pulled along here by the steering electrode. After they get pulled down by the steering electrodes, they're going to hit the anode of this tube, and at the anode of this tube, we have another screen. This is the output phosphor. Those electrons then are getting converted to light. Then after we have that light, we can go through a lens system here. We have a couple of lenses here, and then in between the lenses, we also have an aperture. So the aperture is something that you can fine tune in order to control the amount of light which is hitting your video camera. So that's the last thing here is our video camera. A modern video camera will be either a CCD or a CMOS sensor. Then if we talk about what's going to happen when we do magnification on an image intensifier, you can look first about the case of an unmagnified acquisition. Like we just talked about, your electrons here are traveling in straight lines, again based on the electric fields that are set up by these steering electrodes. And if we actually, again, had a smaller field of view, we could actually change those electric fields. So imagine we do that. If we have a smaller field of view and we change it so the electrons are actually going to still take up the complete area on your phosphor, so that a smaller area here is going to map or be magnified to the same size area here for our phosphor, which is then read out by our video camera. Note that when you use the magnification mode, you actually are going to have a signal which is less bright because you have less total electrons coming in and actually hitting here to make the light signal. Because it's less bright, in order to get enough brightness for your sensor, you actually need to use more X-ray dose. So the advantage is a better magnification leads to better resolution, but the disadvantage is that it's at the cost of a higher radiation dose. Some super fun equations here. Don't worry, it's going to be relatively quick and pain-free. The brightness gain comes from two factors. One is the minification gain, that's a geometry effect, and the other is the flux gain, which is because you're actually imparting more energy on the electrons. You're actually taking the electrons, giving them more kinetic energy that's then going to help get converted into the image signal. The minification gain just goes like the ratio of the areas from the input to the output, and the ratio of the areas will just go like the ratio of the diameters squared. That's the minification gain. The flux gain is just the number of photons at the output divided by the number of photons at the input. The conversion factor is just the output illumination, which will then be the input for the video camera, divided by the exposure, which is the input for your X-ray signal into the image intensifier. And at the back end of your image intensifier, we have this aperture here. You can think about the different settings. If you had your aperture being open here, then you see that all of your light photons are going to end up going through. So this is going to lead to more light hitting on the actual CCD or CMOS sensor. If you want to reduce the light which is getting there, you can actually just close the aperture some, and this will help reduce the actual illumination such that you wouldn't oversaturate the sensor. And then in some scenarios, it's even possible to perform the imaging with a direct coupling so that you wouldn't actually have this aperture at all. You know how the image intensifier works now, and the next video I'm going to have, which I'll have linked up here when it's ready, is a video for a comparison of flat panel detectors with image intensifier with respect to the difference in magnification modes and some details on the spectra and on pulse fluoroscopy for more fun in fluoroscopic imaging.